Hey everyone! Tonight we're going to dive into something that might shift how you think about our place in history. What if everything we've been taught about human civilization, about being the first intelligent species to develop technology, to build cities, to alter the planet, what if that's not quite the whole story? I'm not talking about ancient aliens or anything like that. I'm talking about something much more grounded, yet somehow even more profound. What if we're not the first civilization to emerge on Earth? What if, in the vast sweep of our planet's history, there have been others before us, perhaps many others, who rose, flourished, and eventually disappeared, leaving behind only the faintest traces of their existence? This isn't about proving anything tonight. It's about sitting with a question that, once you really consider it, opens up some fascinating ways of thinking about time, about intelligence, and about the nature of civilization itself. Because when you start to really examine what we know, and more importantly, what we don't know about Earth's deep history, some interesting possibilities begin to emerge. Think about this for a moment. Our planet is about 4.6 billion years old. Complex life has existed for hundreds of millions of years. Yet what we call human civilization, agriculture, cities, written language, the whole package, that's only been around for maybe 10,000 years. Even if you stretch the definition and include the earliest tool use by our ancestors, you're talking about a few million years at most. In the context of Earth's timeline, that's barely a blink. So here's the question that's worth sitting with. In all those billions of years, through all the cycles of climate change, ice ages, asteroid impacts, and continental drift, is it really so impossible that intelligence might have emerged before? That some other form of life might have developed technology, built civilizations, and then vanished so completely that we've found almost no trace of them? Now, I know what some of you might be thinking. If there were previous civilizations, surely we'd have found evidence by now, right? We'd have discovered their ruins, their artifacts, something. But that assumption rests on a few ideas that might be worth questioning. First, it assumes that we'd recognize their technology, or their remains. Second, it assumes that evidence of their existence would have survived the geological processes that have been reshaping our planet for eons. But what if previous civilizations developed along completely different technological paths than ours? What if they worked with biology instead of metals, with living systems instead of mechanical ones? What if their materials and methods were so different from ours that their artifacts would appear to us as nothing more than unusual rocks or organic deposits? And then there's the preservation problem. We like to think our current civilization will leave a lasting mark on the planet, and in some ways it will. But what would actually survive tens of millions of years? Steel corrodes, concrete crumbles, plastics break down, even our nuclear waste, which seems so permanent and dangerous to us, would eventually decay to background levels. The only things that reliably survive in the geological record are very specific types of materials under very specific conditions. Consider this. If our entire industrial civilization disappeared tomorrow, and then 50 million years passed, not an unusual time span in Earth's history, what would remain? Perhaps some unusual spikes in certain isotopes in the geological record. Maybe some compressed carbon layers from our cities. Possibly some scattered fragments of the most chemically stable materials we've created. But recognizable artifacts? Identifiable ruins? The chances would be extraordinarily slim. This isn't pessimism about human achievement, it's just an acknowledgement of how geological time works. The Earth is constantly recycling itself. Erosion, volcanism, plate tectonics, glaciation, these processes are incredibly effective at erasing traces of the past. What strikes us as permanent is often just a temporary arrangement of matter that will eventually be ground down, melted, or buried so deep it might as well not exist. So when we look at the fossil record and the geological evidence, we're seeing only the tiniest fraction of what actually happened. We're looking at the few things that managed to get preserved under exactly the right conditions, in exactly the right places, and then managed to avoid being destroyed by everything that's happened since. It's like trying to reconstruct the entire history of human literature by examining only the few pages that happen to survive a house fire. But here's what makes this question really interesting. It's not just about the past, it's about how we understand intelligence, civilization, and our relationship with the planet. If we really are the first technological civilization Earth has produced, that makes us incredibly special, but also incredibly isolated. We're alone, not just in space, but in time as well, the first of our kind to ever exist. But if we're not the first, if intelligence and civilization are more common in Earth's history than we assume, then we're part of a longer story. We're the latest chapter in a much deeper narrative about how consciousness interacts with the physical world, how living systems can organize themselves into complex societies, how intelligence expresses itself across different forms of life. There's something both humbling and encouraging about that possibility. Humbling because it suggests our achievements might not be as unique as we'd like to think, but encouraging because it implies that intelligence and civilization are robust phenomena, things that can emerge repeatedly under the right conditions, things that are perhaps fundamental expressions of how complex systems organize themselves. Tonight, we're going to explore this question from several angles. We'll look at what we actually know about Earth's history and the development of life. We'll examine some of the anomalies and mysteries in the archaeological and geological record that don't quite fit our standard timeline. We'll consider what kinds of evidence previous civilizations might have left behind, and whether we'd even recognize it if we found it. We'll also think about what this possibility might mean for how we understand our own civilization. If we're not the first, what can we learn from the fact that previous civilizations apparently didn't survive to the present? What does that tell us about the challenges that complex societies face over long time scales? This isn't about reaching definitive conclusions, it's about expanding our sense of what's possible, about questioning assumptions we might not even realize we're making. Because sometimes the most valuable questions aren't the ones that have clear answers, but the ones that open up new ways of thinking about old problems. So let's begin this exploration together. Let's dive into the deep history of our planet and see what mysteries might be waiting there, just beneath the surface of what we think we know. To really understand why the question of previous civilizations is worth considering, we need to step back and appreciate just how vast Earth's history actually is. When we talk about deep time, the kind of timescales geologists and paleontologists work with, we're dealing with numbers that are almost impossible for our minds to truly grasp. Earth formed about 4.6 billion years ago. To put that in perspective, if you compressed all of Earth's history into a single year, complex multicellular life wouldn't appear until sometime in October. Dinosaurs would show up in mid-December, and all of human history, from the first stone tools to space travel, would fit into the last few minutes before midnight on New Year's Eve. This isn't just an abstract exercise in scale. It's a reminder that the conditions for complex life, and potentially for intelligence, have existed on Earth for an almost incomprehensibly long time. For hundreds of millions of years, there have been ecosystems complex enough to support sophisticated organisms, climates stable enough for long-term development, and energy sources abundant enough to fuel the evolution of complex behaviors. Life itself appeared remarkably early in Earth's history. We have evidence of simple microorganisms dating back at least 3.8 billion years, possibly older. For most of Earth's existence, life was microscopic, but even these early organisms were doing some pretty sophisticated things. They were developing photosynthesis, creating the oxygen that would eventually make complex life possible, and establishing the basic biochemical processes that still power every living thing today. The transition to complex, multicellular life happened relatively recently, about 600 million years ago during what we call the Cambrian explosion. This is when we start seeing organisms with specialized organs, complex sensory systems, and sophisticated behaviors. From that point forward, life on Earth has been experimenting with increasingly elaborate forms of organization. What's particularly interesting about this timeline is how it changes our perspective on intelligence. We tend to think of intelligence as something rare and recent, something that took billions of years of evolution to finally achieve. But when you look at the actual progression of life, sophisticated behaviors and problem-solving abilities appear much earlier and more frequently than we might expect. Consider octopuses, for instance. They're incredibly intelligent creatures, capable of using tools, solving complex puzzles, and displaying behaviors that suggest genuine understanding rather than just instinct. Yet their evolutionary lineage diverged from ours hundreds of millions of years ago. They developed their intelligence completely independently, using a radically different body plan and nervous system architecture. This suggests that intelligence isn't a rare fluke that happened once with mammals, but rather a more general property that can emerge from complex neural systems. Dolphins and whales represent another fascinating case. These creatures have brains that are in many ways more complex than ours, with neural structures that have no equivalent in human brains. They display sophisticated social behaviors, tool use, and communication patterns that we're only beginning to understand. Some researchers believe they may have forms of culture and language that are simply too alien for us to readily recognize. But intelligence in the natural world isn't limited to what we traditionally think of as brainy animals. Social insects like ants and bees create incredibly sophisticated societies with division of labor, communication systems, and collective problem-solving abilities that can tackle challenges no individual could handle. Some researchers argue that the real intelligence in these systems isn't located in individual insects, but emerges from the interactions of the colony as a whole. This distributed model of intelligence opens up some intriguing possibilities when we think about prehistoric civilizations. What if intelligence on Earth has taken forms that we wouldn't immediately recognize? What if there have been collective intelligences, or biological computers, or forms of organized behavior so different from our own that we wouldn't think to look for their artifacts? When we examine the fossil record, we find evidence of remarkably sophisticated behaviors going back much further than we might expect. Some of the earliest known tools weren't made by humans or even human ancestors, but by other species entirely. Sea otters have been using stones to crack open shellfish for millions of years. Certain birds have been fashioning complex tools for extracting insects from tree bark for similarly long periods. There's also growing evidence that some extinct species displayed behaviors that suggest forms of intelligence we're only now beginning to appreciate. Certain dinosaur species, for instance, appear to have engaged in sophisticated social behaviors, built complex nests, and may have had communication systems more elaborate than anything we see in modern reptiles. The Triceratops and other ceratopsian dinosaurs developed elaborate bony frills and horns that seem to have served as visual communication devices, allowing for complex social signaling within herds. Some paleontologists suggest these creatures may have had social structures as complex as those of modern elephants or whales, with multi-generational family groups, cooperative child rearing, and sophisticated territorial behaviors. Even more intriguingly, some theropod dinosaurs, the group that includes modern birds, show evidence of behaviors that suggest problem-solving abilities and possibly even primitive tool use. Ravens and crows, their modern descendants, are among the most intelligent animals on the planet, capable of planning for future events, using tools in sequence, and even displaying what appears to be a sense of humor. This brings us to one of the most important questions when considering prehistoric civilizations. What exactly do we mean by civilization? If we define it narrowly, as agriculture, cities, written language, and metal tools, then yes, we're almost certainly the first. But if we think more broadly about organized societies with specialized roles, sophisticated communication, and the ability to modify their environment for collective benefit, then the picture becomes much more complex. Beaver dams, for instance, represent a form of environmental engineering that has profound effects on entire ecosystems. Beavers don't just build dams, they create and maintain complex water management systems that can persist for generations, supporting diverse communities of other species. In some ways, this represents a form of civilization, a species deliberately modifying its environment to create more favorable conditions for itself and its descendants. Coral reefs provide another example of biological engineering on a massive scale. While individual coral polyps are simple organisms, collectively, they create structures that are among the largest living constructions on Earth. These reefs support incredibly complex ecosystems and demonstrate how simple organisms can, through collective action, create environments of remarkable sophistication. But here's where the preservation problem becomes really significant. Beaver dams, no matter how impressive, don't typically survive in the geological record. The wood rots, the stones are scattered by floods, and within a few decades of abandonment, most traces of even the most elaborate beaver engineering projects have vanished. If beavers had built civilization-scale infrastructure, we probably wouldn't know about it. This is the challenge we face when looking for evidence of prehistoric civilizations. Biological materials decompose, wooden structures rot, even stone construction, if it's not built with extremely durable materials and techniques, can be reduced to scattered rubble within relatively short periods. The pyramids of Egypt, which seem so permanent to us, are already showing significant wear after only a few thousand years. Geological processes that operate over millions of years would likely erase even these impressive monuments. The question of what survives over geological time becomes even more complex when we consider the dynamic nature of Earth's surface. Plate tectonics means that oceanic crust is constantly being recycled, with new material forming at mid-ocean ridges and old material being subducted back into the mantle. Most oceanic crust is less than 200 million years old, which means that any evidence of ancient civilizations that might have existed on ocean floors, and remember, much of what's now dry land was once underwater, has likely been destroyed by these geological processes. Continental crust is more stable, but it's subject to its own forms of recycling. Erosion constantly wears down surface features, while volcanic activity can bury or melt anything in its path. Glaciation, which has occurred repeatedly throughout Earth's history, is particularly effective at scouring landscapes clean. The great ice sheets that covered much of North America and Europe as recently as 10,000 years ago obliterated virtually all traces of whatever might have existed on those landscapes before. Even more recent human artifacts demonstrate how quickly evidence can disappear. Archaeological sites that are only a few thousand years old are often difficult to locate and interpret, even when we know roughly where to look for them. Sites from the Pleistocene epoch, the geological period that ended about 12,000 years ago, are rare and fragmentary, preserved only under exceptional circumstances. This creates what paleontologists call preservation bias. We tend to find evidence of life forms and activities that occurred in environments where preservation was likely, in sedimentary deposits, in caves, in areas where rapid burial could protect organic materials from decay. But most of life's activities occur in environments where preservation is unlikely. The vast majority of organisms that have ever lived have left no fossil trace whatsoever. If we apply this same logic to the question of prehistoric civilizations, it suggests that the absence of obvious evidence doesn't necessarily mean such civilizations never existed. It might simply mean that they existed in ways, or in places, or during time periods where preservation was unlikely. They might have used materials that don't survive geological time. They might have built in locations that have since been eroded away, buried under kilometers of sediment, or subducted into the Earth's mantle. This isn't an argument that prehistoric civilizations definitely existed. It's simply an acknowledgement that the conditions for preservation of evidence over geological time are so restrictive that their absence doesn't constitute strong evidence against the possibility. When we're dealing with timescales of tens or hundreds of millions of years, even very robust evidence can be completely erased by natural processes. Now that we've established the vast canvas of Earth's history and the challenges of preservation over geological time, let's examine some of the actual discoveries that make people wonder about our place in the timeline of intelligence. These aren't necessarily proof of anything, but they're puzzling enough to warrant some thoughtful consideration. In 1901, divers working off the Greek island of Antikythera discovered what would become one of archaeology's most perplexing artifacts. Initially dismissed as a corroded piece of bronze, the Antikythera mechanism turned out to be something extraordinary, a complex mechanical computer dating to around 87 BC, capable of predicting the positions of the sun, moon, and planets with remarkable accuracy. The device contains at least 37 bronze gears working together in a sophisticated system that wasn't matched in European technology until astronomical clocks began appearing in the 14th century AD. Think about that timeline for a moment. Here's a piece of ancient Greek technology that demonstrates mechanical sophistication that apparently disappeared from human knowledge for over 1,000 years. The Antikythera mechanism raises some fascinating questions about technological continuity. We tend to think of technological development as a steady upward progression, but what if it's more cyclical than we assume? What if sophisticated knowledge appears, gets lost, and then gets rediscovered? And if this can happen over periods of centuries, what might happen over periods of millennia or longer? This pattern of technological sophistication appearing in unexpected contexts shows up repeatedly in the archaeological record. Take Damascus steel, for instance. This legendary material, produced primarily between 300 and 1700 AD, had properties that modern metallurgists struggled to understand and reproduce. The steel could be forged into blades of extraordinary sharpness and flexibility, with distinctive watered patterns that became the hallmark of the finest medieval weapons. The techniques for making true Damascus steel were lost sometime in the 18th century, and despite centuries of research, we're only now beginning to understand how it was created. The process apparently involved specific combinations of steel with trace amounts of carbon nanotubes and other microscopic structures that weren't formally discovered by modern science until the 20th century. Yet medieval smiths were somehow incorporating these elements into their work through techniques that were passed down through generations and then vanished. Similarly puzzling is the Roman concrete used in structures like the Pantheon, which has not only survived for nearly 2,000 years, but has actually gotten stronger with age. The Romans developed a form of concrete using volcanic ash that creates a self-healing chemical reaction when exposed to seawater. Modern concrete typically begins deteriorating within decades, yet Roman harbor structures that have been submerged for centuries remain remarkably intact. These examples point to a broader pattern: sophisticated techniques and technologies that seem to appear, flourish, and then disappear from human knowledge. While we can explain these cases through cultural transmission and the loss of specialized knowledge, they do make you wonder what other technological capabilities might have existed and been lost over longer timescales. But some discoveries push the boundaries of conventional timelines even further. In 1936, German archaeologist Wilhelm König discovered what appeared to be an ancient battery in Iraq. The Baghdad Battery, as it came to be known, consists of a clay jar containing a copper cylinder and an iron rod dating to around 250 BC. When filled with an acidic solution, the device can generate about 1.1 volts of electricity. Mainstream archaeology generally interprets these objects as storage vessels for sacred scrolls, pointing out that there's no clear evidence they were ever used to generate electricity. But some researchers have noted that similar devices, if used systematically, could have been employed for electroplating, coating objects with thin layers of precious metals. Interestingly, some ancient artifacts do show evidence of what appears to be electroplating, though this technique wasn't officially developed until the 19th century. The question isn't necessarily whether ancient peoples had electric batteries in the modern sense, but whether they might have discovered and utilized electrical phenomena in ways that we don't immediately recognize. After all, electricity itself isn't a modern invention. It's a fundamental property of matter that would have been available to any civilization that learned to harness it. Again, even more intriguing are the precision achievements of ancient builders. The Great Pyramid of Giza, constructed around 2560 BC, was built with an accuracy that's remarkable even by modern standards. The base is leveled to within just 2.1 centimeters across its entire 230-meter width. The sides are aligned to true north with an error of only 3 arc minutes, more accurate than our compass could achieve until the invention of precision instruments. The blocks used in the pyramid's construction were cut and fitted with tolerances measured in millimeters. Some of the interior chambers are built with granite blocks weighing up to 80 tons, transported from quarries hundreds of kilometers away and positioned with extraordinary precision. The king's chamber is constructed with such accuracy that its corners are square to within 2 millimeters. This level of precision isn't limited to Egypt. The stone blocks at Sacsayhuaman in Peru are fitted together so tightly that you can't slide a piece of paper between them, despite some blocks weighing over 100 tons and having complex, irregular shapes with multiple angles and curves. The precision required to achieve this level of fit, especially with such massive stones, challenges our assumptions about ancient capabilities. At Pumapunku in Bolivia, archaeologists find stone blocks cut with such precision that they appear to have been machined. Some blocks have perfectly straight edges, exact right angles, and surfaces so smooth and flat that they meet engineering tolerances typically associated with modern machine tools. The stones are made of andesite, a volcanic rock that's extremely hard and difficult to work with even using modern equipment. What makes these achievements particularly puzzling is that they often represent the most sophisticated work produced by these civilizations, appearing early in their architectural traditions rather than as the culmination of centuries of development. It's as if the knowledge of how to achieve such precision appeared fully formed and then, in many cases, was gradually lost over time. The conventional explanation is that these ancient builders developed sophisticated techniques, using the tools and materials available to them, combined with enormous amounts of skilled labor and time. This is certainly possible and demonstrates the remarkable ingenuity of ancient peoples, but it also raises questions about what other capabilities these civilizations might have possessed that haven't survived in the archaeological record. Consider the case of Greek fire, the incendiary weapon used by the Byzantine Empire from the 7th to the 14th centuries AD. This substance could burn on water and was nearly impossible to extinguish, giving Byzantine naval forces a significant advantage in maritime warfare. The formula was so closely guarded that it was eventually lost entirely, and despite centuries of research, modern chemists have never definitively recreated the original substance. If a military technology that was actively used for centuries can be completely lost, what might happen to other forms of knowledge over much longer periods? And if we're missing important technologies from just 1,000 years ago, how much might we be missing from 10,000 or 100,000 years ago? The dating of these anomalous artifacts and achievements often relies on the archaeological context in which they're found, the layers of soil, the associated artifacts, the stylistic comparisons with other known objects from the same period. But this approach assumes that the context accurately reflects the age of the object itself. What if some of these artifacts are much older than their archaeological context suggests? What if they represent knowledge that was preserved and passed down through many generations before being incorporated into later constructions? This possibility becomes more intriguing when we consider how often ancient texts and traditions refer to receiving knowledge from earlier sources. Egyptian texts frequently mention the followers of Horus, a group of wise beings who supposedly preserved knowledge from a much earlier time. Mesopotamian texts describe the Apkallu, 7 wise beings who brought civilization to humanity after a great flood. Hindu traditions speak of previous yugas or ages, each with their own level of technological and spiritual development. While these accounts are generally interpreted as mythology, they consistently describe a pattern of rise and fall, of knowledge being preserved through catastrophic periods and then transmitted to later civilizations. What if these stories contain some historical memory of actual technological capabilities that were lost and then partially recovered? The Vedic texts of ancient India, for instance, contain remarkably sophisticated descriptions of what appear to be flying vehicles called vimanas, complete with technical specifications for their construction and operation. While these are typically dismissed as mythology, the level of technical detail is unusually specific for purely imaginary devices. Some researchers have noted that certain descriptions correspond surprisingly well to principles of aerodynamics and propulsion that weren't formally understood until modern times. Similarly, ancient Chinese texts describe flying vehicles and advanced weapons with considerable technical precision. The Liezi, written in the 4th century BC, contains descriptions of artificial men and flying machines that read more like engineering manuals than fantasy literature. While we shouldn't jump to conclusions about ancient flying machines, the consistency and technical detail of these accounts across different cultures is worth noting. These textual anomalies become particularly interesting when combined with certain archaeological discoveries that don't quite fit conventional timelines. Gold artifacts discovered in Colombia and Peru appear to depict flying vehicles with remarkable resemblance to modern aircraft, complete with what look like cockpits, wings, and tail fins. While these are generally interpreted as stylized birds or insects, some researchers have noted that they possess aerodynamic properties that suggest familiarity with principles of flight. When aeronautical engineers have analyzed some of these artifacts, they've found that they possess characteristics, such as vertical stabilizers and swept wings, that are specifically associated with powered flight rather than the natural flight of birds. Bird wings are designed for flapping flight and have very different structural requirements than the fixed wings of aircraft. None of this proves that ancient civilizations possessed flying machines, but it does suggest that ancient peoples might have been more sophisticated observers of aerodynamic principles than we typically assume. And if they were making such detailed observations of flight characteristics, what other natural phenomena might they have studied and understood in ways that we haven't fully appreciated? The preservation bias we discussed earlier becomes particularly relevant when considering advanced technologies. Most of our assumptions about ancient capabilities are based on what has survived: stone tools, pottery, metal objects, and architectural remains. But what if the most sophisticated technologies of ancient civilizations were made from materials that don't preserve well? What if they worked with biological systems, organic compounds, or chemical processes that leave little or no trace in the archaeological record? Modern biotechnology demonstrates that living systems can be engineered to perform remarkably sophisticated functions. Bacteria can be programmed to produce complex chemicals, plants can be modified to create new materials, and biological computers can process information using DNA. If ancient civilizations had developed along biotechnological rather than mechanical lines, their most advanced achievements might be completely invisible to archaeology. This possibility becomes more intriguing when we consider that many traditional technologies around the world do involve sophisticated manipulation of biological systems. Traditional fermentation processes can produce materials with remarkable properties. Certain plants can be processed to create substances stronger than steel. Indigenous peoples worldwide have developed chemical processes using natural materials that modern chemistry is only beginning to understand. The question isn't whether ancient peoples possessed modern-style technology, but whether they might have developed sophisticated capabilities using different approaches and materials than we would expect. If so, the absence of recognizable artifacts might not indicate the absence of advanced knowledge, but simply the use of different technological paradigms that haven't been preserved or recognized. Moving beyond individual artifacts, let's explore some larger patterns and discoveries that push the boundaries of what we expect to find in the archaeological and geological record. These are phenomena that, while not necessarily proving the existence of prehistoric civilizations, certainly make us question some of our assumptions about the past. One of the most intriguing categories of anomalies involves structures that appear artificial but are found in contexts that challenge conventional dating. The Yonaguni Monument off the coast of Japan provides a fascinating case study. Discovered in 1986 by diving instructor Kihachiro Arataki, this underwater structure features what appear to be terraced platforms, stairs, and geometric formations carved from solid rock. The monument sits at depths of 25 to 40 meters in an area that would have been above sea level during the last ice age, which ended approximately 12,000 years ago. If the structures are indeed artificial, they would have been created when the area was dry land, making them potentially older than any known monumental architecture. Marine geologist Masaki Kimura of the University of the Ryukyus has spent decades studying the site and argues that many features show clear signs of human modification. He points to right angles, straight edges, and stepped formations that would be extremely unlikely to occur naturally in the local sandstone. The structures include what appear to be roads, steps, and even what looks like a large amphitheater carved into the rock. However, other researchers, including Boston University's Robert Schoch, suggest that the formations could be entirely natural, created by tectonic activity and erosion patterns typical of the region's geology. The sandstone in the area does fracture along natural lines that can create geometric patterns, and underwater erosion can produce formations that might appear artificial to human observers. What makes the Yonaguni debate particularly interesting is how it illustrates the challenge of interpreting evidence that exists at the very edge of what we expect to find. Whether the structures are natural or artificial, they remind us that vast areas of the Earth's surface that were once dry land are now underwater, and we've barely begun to explore what might be preserved beneath the waves. This underwater preservation issue extends far beyond Yonaguni. During the last ice age, sea levels were approximately 120 meters lower than they are today. Enormous areas of what is now continental shelf were dry land, including vast coastal plains where early civilizations would likely have developed. The Doggerland region, which once connected Britain to continental Europe, covered an area roughly the size of England and supported rich ecosystems and human populations for thousands of years before being submerged. As sea levels rose at the end of the Ice Age, these coastal regions would have been gradually flooded, potentially preserving any structures or settlements that had been built there. Yet, underwater archaeology is expensive and technically challenging, so we've only explored a tiny fraction of these submerged landscapes. What we have found suggests that these areas were indeed heavily populated and might contain significant archaeological sites. Off the coast of India, marine archaeologists have discovered what appear to be the remains of ancient settlements at depths that indicate they were flooded thousands of years ago. The structures include walls, courtyards, and what appear to be planned urban layouts. While dating these underwater sites is challenging, they suggest that sophisticated settlements existed in areas that are now completely submerged. Similar discoveries have been made in the Mediterranean, where underwater surveys have revealed harbor installations, roads, and building foundations at depths indicating submersion during historical times. Some of these sites appear to represent urban planning and engineering capabilities that exceed what we might expect for their apparent age. But the anomalies aren't limited to underwater sites. On land, researchers continue to discover structures and formations that challenge conventional timelines. Göbekli Tepe in Turkey, discovered in the 1960s but not fully excavated until recent decades, has revolutionized our understanding of early human capabilities. Dating to approximately 11,600 years ago, the site features massive stone pillars arranged in circles, decorated with sophisticated carvings of animals and abstract symbols. What makes Göbekli Tepe so significant is that it predates the development of agriculture and permanent settlements. According to conventional archaeological timelines, hunter-gatherer societies shouldn't have had the social organization or resources necessary to construct such elaborate monuments. Yet here's clear evidence that they did, suggesting that our assumptions about the capabilities of pre-agricultural societies might need significant revision. The site required enormous coordination and labor. The largest pillars weigh up to 20 tons and were quarried, transported, and erected using techniques that we're still trying to understand. The carvings are sophisticated and consistent across the site, suggesting a shared symbolic system and artistic tradition. Most puzzling of all, the site appears to have been deliberately buried around 8000 BC, preserved under tons of soil for millennia. This pattern of sophisticated construction appearing much earlier than expected shows up in other locations as well. The temple complexes of Malta, dating to between 3600 and 2300 BC, demonstrate architectural and engineering knowledge that seems remarkably advanced for their time. These megalithic structures include precise acoustic chambers, sophisticated corbelled roofing, and evidence of advanced planning and construction techniques. What's particularly intriguing about the Maltese temples is their acoustic properties. The chambers appear to have been designed to amplify and focus sound in specific ways, with resonant frequencies that correspond to ranges known to have psychological and physiological effects. Modern acoustic analysis has revealed that the temples can amplify male voices while filtering out higher frequencies, and that certain chambers produce infrasound, frequencies below the range of human hearing that can induce altered states of consciousness. These acoustic properties suggest that the builders had a sophisticated understanding of sound and its effects on human consciousness. While this knowledge could have been developed through trial and error over many generations, it does indicate capabilities that we might not expect from Neolithic societies. Even more puzzling are discoveries that suggest knowledge of astronomical phenomena that shouldn't have been observable without sophisticated instruments. The Antikythera mechanism, which we discussed earlier, required not only mechanical sophistication, but also precise astronomical knowledge. The device could predict eclipses, track the movements of planets, and calculate the timing of Olympic Games based on complex calendrical calculations. But the astronomical knowledge embedded in ancient monuments and artifacts often goes beyond what could be observed with the naked eye. The Maya calendar, for instance, tracked cycles of Venus, Mars, and other planets with accuracy that required centuries of careful observation. Their calculations of the solar year were more accurate than the Julian calendar used in Europe until the 16th century. Similarly, the builders of Stonehenge encoded astronomical alignments that suggest detailed knowledge of celestial mechanics. The monument aligns not only with obvious phenomena like the summer and winter solstices, but also with more subtle cycles like the 18.6-year lunar standstill cycle and the movements of specific stars. What's particularly interesting is that many of these astronomical alignments involve cycles that take decades or centuries to complete. Tracking such patterns would require not only sophisticated observation techniques, but also systems for preserving and transmitting knowledge across many generations. This suggests forms of institutional continuity and knowledge preservation that seem remarkably advanced for supposedly primitive societies. The precision of these astronomical observations becomes even more remarkable when we consider the tools available to ancient astronomers. Without telescopes or precision instruments, they somehow managed to track celestial movements with accuracy that approaches modern measurements. This suggests either observational techniques that we don't fully understand or instruments that haven't survived in the archaeological record. Some researchers have proposed that ancient astronomical observations might have been aided by water-based instruments, pools or basins that could act as primitive telescopes by reducing atmospheric distortion. Others suggest that certain stone circles and alignments might have functioned as large-scale astronomical instruments, using the landscape itself as a measuring device. These possibilities become more intriguing when we consider that precision measurement and astronomical observation are fundamental requirements for navigation, agriculture, and timekeeping, all essential technologies for complex civilizations. If ancient peoples possessed sophisticated astronomical knowledge, they might have had other advanced capabilities that we haven't recognized or that haven't been preserved. The question of precision tools and measurement techniques extends beyond astronomy. Many ancient constructions demonstrate levels of accuracy that seem to require sophisticated measuring instruments. The Great Pyramid, for instance, incorporates mathematical relationships like pi and the golden ratio with precision that suggests advanced geometric knowledge. But perhaps even more puzzling are discoveries that suggest knowledge of geographical features that supposedly weren't known until much later periods. The Piri Reis map, created in 1513 by Ottoman Admiral Piri Reis, shows the coastline of Antarctica with remarkable accuracy, despite the continent not being officially discovered until 1820. The map appears to show Antarctica without its ice cover, revealing geographical features that weren't confirmed until 20th century seismic surveys. While the map could be based on earlier sources that have since been lost, its accuracy raises questions about what geographical knowledge might have existed in ancient times. If ancient peoples had detailed knowledge of distant continents and geographical features, it suggests navigation and exploration capabilities that exceed what we typically assume for pre-modern civilizations. Similar geographical anomalies appear in other ancient maps and texts. Chinese maps from the Han Dynasty show geographical knowledge that seems remarkably accurate for their time, including details of coastlines and inland features that wouldn't be systematically mapped until much later periods. Some of these maps show regions that were supposedly unknown to Chinese civilization at the time they were created. The preservation of this kind of knowledge raises interesting questions about information transmission across long time periods. Maps and geographical knowledge are practical tools that need constant updating and verification to remain useful. If ancient maps show accurate details of distant regions, it suggests not only that these areas were explored and mapped, but that the knowledge was preserved and transmitted through whatever political and cultural changes occurred in the intervening centuries. This pattern of preserved ancient knowledge extends to other domains as well. Traditional metallurgy, medicine, and chemistry around the world often demonstrate understanding of principles that weren't formally recognized by Western science until relatively recent times. Traditional Chinese medicine, for instance, includes sophisticated understanding of physiological processes and chemical interactions that modern research is only beginning to validate scientifically. Similarly, traditional metallurgical techniques from various cultures demonstrate knowledge of chemical processes and material properties that suggest sophisticated understanding of chemistry and physics. The Damascus steel we discussed earlier is just one example of traditional techniques that exceeded the capabilities of later periods. What makes these examples particularly intriguing is that they often represent knowledge that was preserved through oral tradition rather than written records. This suggests that sophisticated technical knowledge can be maintained and transmitted across many generations without formal educational institutions or written documentation. If this kind of knowledge preservation was possible in historical times, it might have been possible over much longer periods as well. The question of knowledge preservation becomes particularly interesting when we consider the possibility of intentional concealment or protection of important information. Many traditional societies have elaborate systems for protecting sacred or dangerous knowledge, restricting access to information that could be harmful if misused or lost if shared too widely. These knowledge preservation systems often involve multiple redundancies, oral traditions, symbolic representations, practical demonstrations, and ritual enactments that ensure important information survives even if some transmission methods are disrupted. If ancient civilizations possessed advanced knowledge, they might have developed similar systems for preserving it through periods of decline or catastrophe. The evidence we've examined in this act doesn't prove the existence of prehistoric civilizations, but it does suggest that our assumptions about ancient capabilities might be incomplete. Whether we're looking at underwater structures, astronomical knowledge, precision construction, or geographical understanding, we consistently find examples of sophistication that pushes the boundaries of what we expect from supposedly primitive societies. These anomalies don't necessarily require extraordinary explanations, but they do require us to expand our sense of what was possible in the past. They suggest that the development of human knowledge and capability might have been less linear and more complex than we typically assume, with periods of advancement and decline that could have produced capabilities we haven't fully recognized or understood. Now that we've examined some of the puzzling evidence and anomalies, let's explore some of the theories that researchers have proposed to explain these mysteries. These aren't necessarily conclusions we should accept uncritically, but they represent different ways of thinking about the evidence we've discussed, and they're worth considering as intellectual exercises, if nothing else. One of the most thoughtful approaches to the question of prehistoric civilizations comes from the concept of cyclical development. This idea suggests that human civilization, rather than following a straight line of progress from primitive to advanced, might actually follow cycles of rise, decline, and renewal that play out over much longer timescales than we typically consider. The cyclical model isn't entirely speculative. We can see examples of technological and social regression in recorded history. The Bronze Age collapse around 1200 BC saw the fall of several major civilizations around the Mediterranean, leading to a period often called the Dark Ages, where writing systems were lost, trade networks collapsed, and technological capabilities declined significantly. It took centuries for the region to regain the level of sophistication that had existed before the collapse. Similarly, the fall of the Roman Empire led to a period where many technological capabilities were lost in Europe. Roman concrete techniques, road-building methods, and engineering knowledge largely disappeared, not to be fully recovered until much later periods. Even more dramatically, the Library of Alexandria, which represented one of humanity's greatest repositories of knowledge, was gradually destroyed over several centuries, taking with it countless works of science, mathematics, and philosophy that have never been recovered. If such dramatic losses of knowledge and capability can occur over periods of centuries, what might happen over periods of millennia or tens of millennia? The cyclical theory suggests that human civilization might have achieved significant sophistication multiple times in the past, only to have that sophistication lost due to natural catastrophes, climate change, war, or other disruptions. This model becomes particularly interesting when we consider the impact of ice ages on human development. The last glacial maximum, which occurred around 20,000 years ago, would have made large portions of the northern hemisphere uninhabitable and forced human populations into refuge areas around the equator and in more temperate regions. Any civilizations that had developed in the ice-covered areas would have been completely destroyed, while populations that survived in refuge areas might have lost much of their accumulated knowledge and technology due to the disruption. But ice ages are cyclical phenomena that have occurred repeatedly throughout Earth's history. The current interglacial period, which began about 12,000 years ago, is just the latest in a series of warm periods separated by much longer ice ages. Each transition between glacial and interglacial periods would have represented a massive disruption to any existing human societies, potentially causing cycles of advancement and regression that could extend back much further than our current archaeological record suggests. The geological evidence for these climatic cycles is clear and well established. What's more speculative is whether human societies might have achieved significant sophistication during previous interglacial periods. But when you consider that previous interglacials lasted for thousands or tens of thousands of years, plenty of time for complex societies to develop, the possibility becomes worth considering. Some researchers have proposed even more dramatic scenarios involving catastrophic events that could reset technological development. The Younger Dryas impact hypothesis, for instance, suggests that a cosmic impact around 12,800 years ago triggered rapid climate change and mass extinctions at the end of the last ice age. While this hypothesis remains controversial, it illustrates how sudden catastrophic events could potentially disrupt even advanced civilizations. Asteroid impacts, supervolcanic eruptions, gamma-ray bursts, and other cosmic events occur on timescales that are much longer than human history, but short enough to have affected Earth multiple times over geological timescales. Each such event could potentially cause what researchers call a bottleneck in human development, forcing surviving populations to start over with reduced numbers and limited resources. The Toba supervolcanic eruption, which occurred around 74,000 years ago, appears to have reduced the global human population to perhaps as few as 10,000 individuals. Such severe population bottlenecks would inevitably lead to the loss of accumulated knowledge and technology, as surviving groups would be focused primarily on basic survival rather than maintaining complex cultural achievements. If similar bottlenecks occurred multiple times in human history, they could explain both the development and the loss of sophisticated capabilities over long timescales. Populations that survived these events might retain fragments of earlier knowledge, preserved in myths, oral traditions, or practical techniques, but lose the larger context and systematic understanding that would allow them to fully recreate their previous achievements. This fragmented preservation of knowledge appears in many traditional cultures. Australian Aboriginal Dreamtime stories, for instance, contain what appear to be accurate descriptions of geographical features and events that occurred tens of thousands of years ago, including details of coastlines that were submerged at the end of the last ice age. Similarly, flood myths appear in cultures around the world and often contain remarkably consistent details despite the geographical separation of these cultures. While these stories are typically interpreted as mythology, some researchers suggest they might represent cultural memories of actual events, passed down through oral tradition over extraordinarily long periods. If oral traditions can preserve accurate information for tens of thousands of years, they might also preserve technological or scientific knowledge from earlier periods. The Hindu concept of yugas, or world ages, provides an interesting framework for thinking about these cyclical patterns. According to this tradition, human civilization goes through repeating cycles of 4 ages: the Satya Yuga, or Golden Age, characterized by high spiritual and technological development; the Treta Yuga, where knowledge begins to decline; the Dvapara Yuga, where further deterioration occurs; and the Kali Yuga, or Dark Age, where knowledge and capability reach their lowest point before the cycle begins again. While we shouldn't take these ancient cosmologies literally, they do represent sophisticated thinking about how civilizations rise and fall over very long timescales. The texts that describe these cycles often include remarkably detailed technical information, suggesting that whoever developed these concepts had access to advanced knowledge that was being preserved through periods of decline. The Vedic texts, for instance, contain mathematical and astronomical information that wasn't formally rediscovered in the West until much later periods. They include accurate calculations of planetary periods, sophisticated understanding of mathematics and geometry, and detailed descriptions of what appear to be advanced technologies. While these texts are generally dated to around 1500 BC, they claim to preserve knowledge from much earlier periods. But cyclical theories don't necessarily require human civilizations to be responsible for all the anomalies we've discussed. Some researchers have proposed that intelligence might have evolved independently in other species at various points in Earth's history, possibly developing forms of civilization that followed completely different technological pathways than our own. This possibility becomes more plausible when we consider how intelligence has evolved multiple times independently in different lineages. Octopuses, as we mentioned earlier, developed sophisticated cognitive abilities completely independently from vertebrates. Their nervous systems are organized in fundamentally different ways than mammalian brains, yet they demonstrate problem-solving abilities, tool use, and even what appears to be individual personality and creativity. Dolphins and whales represent another independent evolution of advanced intelligence. These creatures have brains that are in many ways more complex than human brains, with neural structures that have no equivalent in terrestrial mammals. They demonstrate sophisticated social behaviors, complex communication systems, and problem-solving abilities that we're only beginning to understand. Some researchers have speculated about what forms of civilization these marine intelligences might have developed if they had had access to fire and tool-making materials. Their social structures are already remarkably complex, with multi-generational family groups, cultural transmission of knowledge, and cooperative hunting strategies that require sophisticated planning and communication. But marine environments pose obvious challenges for the development of technology as we understand it. Without fire, metallurgy becomes impossible. Without solid surfaces to build on, permanent structures are difficult to create. However, these limitations might simply mean that aquatic civilizations would develop along completely different technological lines. Biotechnology might be a natural pathway for intelligent species that evolved in aquatic environments. Living systems can be modified and directed to perform complex functions, and many marine organisms already demonstrate remarkable biological engineering capabilities. Coral reefs, for instance, represent massive construction projects carried out by colonies of simple organisms working together over many generations. If an intelligent aquatic species had learned to direct and modify biological systems the way we direct mechanical systems, they might be able to create sophisticated technologies that would leave little trace in the geological record. Biological computers, living buildings, and organic machines would all decompose completely within relatively short periods, leaving no evidence of their existence. This biotechnological pathway might not be limited to aquatic species. Terrestrial organisms also demonstrate remarkable biological engineering capabilities. Termite colonies create complex ventilation systems that maintain precise temperature and humidity control. Beaver dams represent sophisticated water management projects that can persist for generations. Some plants have evolved complex chemical processes that produce materials with remarkable properties. An intelligent species that develop biotechnology rather than mechanical technology might be able to achieve considerable sophistication while leaving very little evidence that would be recognizable to archaeologists. Their most advanced achievements might appear to us as nothing more than unusual biological specimens or chemical deposits. Even more speculatively, some researchers have proposed that intelligence might develop at scales that we don't typically consider. Just as individual cells can organize into complex multicellular organisms, individual organisms might organize into collective intelligences that operate at ecosystem or even planetary scales. This idea isn't entirely without precedent. Slime molds, despite being single-celled organisms, can solve complex optimization problems when foraging for food, finding efficient pathways between food sources that rival the performance of sophisticated algorithms. Ant colonies demonstrate collective decision-making capabilities that no individual ant possesses, with the colony as a whole able to solve problems that would be impossible for individual insects. If intelligence can emerge at these collective scales, it might be possible for entire ecosystems to develop forms of information processing and problem solving that we wouldn't recognize as intelligence because they operate so differently from individual consciousness. Such collective intelligences might be able to manipulate their environment in sophisticated ways while leaving no artifacts that we would interpret as technology. These speculative possibilities remind us that our understanding of intelligence itself is still quite limited. We tend to define intelligence in terms that are familiar to us: individual consciousness, tool use, language, and so forth. But intelligence might be a much more general phenomenon that can emerge in forms that we haven't yet learned to recognize. When we apply this expanded understanding of intelligence to the question of prehistoric civilizations, it opens up possibilities that go far beyond simply asking whether humans developed advanced technology in the past. It raises questions about what forms of intelligence might have emerged over Earth's long history, what kinds of civilizations they might have created, and whether we would even recognize evidence of their existence if we found it. The timeframes involved in these speculations are genuinely staggering. Complex life has existed on Earth for hundreds of millions of years. That's hundreds of millions of years during which intelligence could potentially have emerged, developed sophisticated capabilities, and then disappeared, leaving little or no trace in the geological record. Even if such developments were extremely rare, occurring perhaps once every 10 or 50 million years, there could still have been dozens of intelligent species in Earth's history. Each might have followed different evolutionary pathways, developed different forms of technology, and faced different challenges and opportunities. The absence of obvious evidence for such civilizations doesn't necessarily argue against their existence. As we've discussed, the preservation of evidence over geological time is extremely difficult. Most of what happens on Earth's surface leaves no permanent trace. Even dramatic events like massive volcanic eruptions or asteroid impacts can be difficult to detect in the geological record after sufficient time has passed. Moreover, if previous intelligent species developed along different technological pathways than our own, their artifacts might not be recognizable to us as technology. We're trained to look for tools and structures that resemble our own, but intelligence might express itself in forms that are completely alien to our experience. These theoretical possibilities don't constitute evidence for prehistoric civilizations, but they do suggest that the question is more complex and interesting than it might initially appear. They remind us that intelligence, technology, and civilization might be much more diverse phenomena than our single example suggests, and that the universe of possibilities is much larger than we typically imagine. After exploring some of the more speculative theories about prehistoric civilizations, it's worth stepping back and examining how mainstream science explains the anomalies and mysteries we've been discussing. These explanations don't necessarily close the door on all possibilities, but they do provide grounded perspectives that help us think more clearly about what the evidence actually tells us. The scientific method has served us well precisely because it demands rigorous evidence and careful reasoning before accepting extraordinary claims. When archaeologists, geologists, and other researchers encounter anomalous findings, they typically look first for explanations that fit within our current understanding of how natural and human systems work. This conservative approach has prevented many false conclusions and has gradually built up a reliable body of knowledge about the past. Take the Antikythera mechanism, which we discussed earlier, as an example of seemingly anachronistic technology. While the device is indeed remarkably sophisticated for its time, mainstream archaeology doesn't see it as evidence of lost super technology or prehistoric civilizations. Instead, it represents a logical development within the context of Greek mathematical and mechanical knowledge of the period. The Greeks had already developed sophisticated mathematical concepts, including geometric principles that could be applied to mechanical problems. They understood gear ratios, had experience with precision metalworking, and possessed astronomical knowledge that was quite advanced for its time. The Antikythera mechanism represents the culmination of these existing capabilities, not an impossible leap beyond them. What made the device seem so anomalous was our underestimation of ancient Greek technological capabilities, not evidence that they possessed knowledge beyond what we would expect. When researchers began studying the mechanism in detail, they found that while it was extraordinarily clever, it was built using techniques and materials that were available in the ancient world. This pattern of initially underestimating ancient capabilities appears repeatedly in archaeology. We tend to assume that technological development follows a linear progression, with each innovation building directly on previous ones in a predictable sequence. But actual technological development is much more complex, with occasional dramatic advances followed by periods of stagnation or even regression. The loss of Damascus steel techniques provides a good example of how sophisticated knowledge can disappear even in historical times. The techniques weren't lost because they were impossible or supernatural, but because they depended on specific combinations of materials, trade routes, and skilled craftspeople. When the political and economic conditions that supported this technology changed, the knowledge was gradually lost. Modern metallurgists have now largely figured out how Damascus steel was made, and it turns out to involve perfectly natural chemical processes. The distinctive patterns and superior properties resulted from the formation of carbon nanotubes and other microscopic structures within the steel, created by specific forging techniques combined with particular types of raw materials from certain geographical regions. The Romans' self-healing concrete presents a similar case. While the material does have remarkable properties, research has shown that it relies on well-understood chemical reactions involving volcanic ash and lime. The Romans developed this technology through centuries of practical experience and experimentation, not through impossible knowledge of advanced chemistry. What makes these examples particularly instructive is that they demonstrate how sophisticated technologies can emerge through accumulated practical knowledge without requiring theoretical understanding that exceeds the scientific capabilities of their time. Ancient craftspeople were often extraordinarily skilled observers who could detect subtle relationships and patterns that allowed them to develop effective techniques without necessarily understanding the underlying scientific principles. This empirical approach to technological development could explain many of the precision achievements we see in ancient construction. The builders of the Great Pyramid didn't need modern surveying equipment to achieve extraordinary accuracy. They needed careful observation, practical experience, and probably a great deal of time and patience. Traditional craftspeople working with simple tools can achieve remarkable precision when they have sufficient skill and motivation. The acoustic properties of ancient structures like the Maltese temples also yield to conventional explanations when examined carefully. Sound behavior follows well-understood physical principles, and structures with specific proportions and materials will naturally have certain acoustic characteristics. Ancient builders working through trial and error over many generations could have discovered these properties without needing advanced theoretical knowledge of acoustics. Moreover, we should be cautious about assuming that all acoustic effects were intentional. Structures built for other purposes might accidentally have interesting acoustic properties that later populations interpreted as evidence of advanced knowledge. The human tendency to find patterns and meaning in natural phenomena is powerful, and we might be reading more intentionality into ancient designs than actually existed. The precision astronomical knowledge embedded in many ancient monuments and artifacts also has conventional explanations that don't require lost super-civilizations. Careful observation of the sky over many generations can yield remarkably precise understanding of celestial cycles. Ancient peoples had strong practical motivations for developing this knowledge. Agriculture, navigation, and timekeeping all depend on accurate understanding of astronomical patterns. What we sometimes interpret as impossible precision in ancient astronomical knowledge often reflects the accumulated observations of many generations of skywatchers, combined with mathematical techniques that were sophisticated but not beyond the capabilities of ancient mathematicians. The Maya calendar system, for instance, represents centuries of careful observation and calculation, but it was built using mathematical concepts that were well within Maya capabilities. The underwater structures that some interpret as evidence of prehistoric civilizations also have more conventional explanations. Natural geological processes can create formations that appear artificial to human observers, especially when those formations are viewed underwater where perspective and scale are difficult to judge. The Yonaguni Monument, for example, lies in a region with active tectonics and distinctive geological characteristics. The local sandstone naturally fractures along straight lines when subjected to stress, and underwater erosion can create sharp edges and geometric patterns. While some features of the site are certainly unusual, they don't necessarily require human intervention to explain. This doesn't mean that all underwater structures are natural, but it does suggest that we should be cautious about interpreting underwater formations as artificial without very strong evidence. The psychological tendency to see human design in natural patterns is particularly strong when we're examining unfamiliar environments like underwater landscapes. The geographical knowledge that appears in some ancient maps also has explanations that don't require prehistoric civilizations or impossible ancient exploration. Maps are often based on earlier sources, and geographical knowledge can be transmitted through trade routes and cultural contact even when direct exploration doesn't occur. The Piri Reis map, which appears to show Antarctica without ice cover, might be based on much earlier sources that have since been lost. But it's also possible that the map shows a different geographical feature altogether, or that the apparent accuracy is partly coincidental. When you're dealing with partial and distorted maps from historical periods, it's easy to see patterns that might not actually be there. Even if some ancient maps do show accurate knowledge of distant regions, this doesn't necessarily require advanced civilizations. It could simply reflect more extensive ancient exploration and trade than we typically assume. Human societies have been remarkably mobile throughout history, and long-distance travel was more common in ancient times than many people realize. The pattern of sophisticated knowledge appearing and then disappearing also has conventional explanations that don't require cyclical civilizations or catastrophic resets. Knowledge transmission in pre-literate societies is inherently fragile, depending on chains of teachers and students that can be broken by war, disease, migration, or social disruption. Even in literate societies, knowledge can be lost when the institutions that preserve it are destroyed or when the social conditions that support specialized learning disappear. The loss of classical knowledge during the European Dark Ages illustrates how even written knowledge can disappear when the cultural context that supports it is disrupted. Traditional knowledge systems around the world demonstrate both the possibility of preserving sophisticated information over long periods and the fragility of such preservation. Indigenous peoples have maintained detailed knowledge of local ecosystems, medicinal plants, and technical skills for thousands of years through oral tradition. But this same knowledge can be lost within a single generation if the transmission process is interrupted. The biological and technological capabilities that some researchers attribute to prehistoric civilizations also have more conventional explanations. Traditional biotechnology is indeed remarkably sophisticated in many cultures, but it represents the accumulated practical knowledge of many generations working with biological systems, not advanced theoretical understanding that exceeds natural capabilities. Similarly, traditional materials science and chemistry often involve sophisticated understanding of natural processes, but this understanding developed through empirical observation and experimentation rather than through impossible theoretical knowledge. When traditional techniques seem to exceed modern capabilities, it's usually because modern science has focused on different approaches rather than because traditional knowledge was somehow supernatural. The challenges of dating ancient sites and artifacts also contribute to some of the apparent anomalies in the archaeological record. Dating techniques all have limitations and sources of error, and the interpretation of archaeological contexts can be complex and uncertain. Radiocarbon dating, for instance, requires organic material and can be affected by contamination from older or younger carbon sources. Geological dating methods work well for very ancient materials, but become less precise for more recent periods. Contextual dating based on associated artifacts and stratigraphic relationships requires careful interpretation and can be complicated by site disturbance or reuse. These limitations don't invalidate archaeological dating, but they do mean that some apparently anomalous dates might reflect methodological issues rather than genuine chronological mysteries. When artifacts appear in unexpected contexts, it's often more likely that there are issues with dating or context interpretation than that the artifacts represent evidence of prehistoric super civilizations. The preservation bias we discussed earlier also plays a major role in shaping our understanding of ancient capabilities. We tend to find evidence of the most durable and distinctive aspects of ancient cultures while missing the more perishable but potentially more sophisticated elements. Stone tools and pottery survive well in the archaeological record, so we have extensive evidence of these technologies. But textiles, wooden implements, organic chemicals, and biological technologies are much less likely to survive. So our picture of ancient capabilities is skewed toward the most durable technologies rather than necessarily the most advanced ones. This preservation bias might make ancient peoples appear more primitive than they actually were, but it doesn't necessarily support the existence of lost super technologies. Instead, it suggests that ancient societies probably had a broader range of capabilities than the archaeological record directly shows, but those capabilities likely involved sophisticated use of perishable materials rather than impossible technologies. The statistical issues involved in evaluating anomalous claims also deserve consideration. When you examine thousands of archaeological sites, geological formations, and historical artifacts, you would expect to find some that appear anomalous just by chance. The interesting question isn't whether anomalies exist, but whether they occur more frequently than we would expect from normal variation and methodological uncertainty. Most claimed anomalies, when examined carefully, fall within the range of what we might expect from natural variation, measurement uncertainty, and the limitations of our knowledge about ancient capabilities. The few that remain genuinely puzzling are interesting and worth investigating, but they don't necessarily require extraordinary explanations. The psychological factors that influence how we interpret evidence also play important roles in evaluating claims about prehistoric civilizations. Humans are naturally pattern-seeking creatures who tend to see design and intentionality even in random phenomena. We're also prone to confirmation bias, paying more attention to evidence that supports our existing beliefs while downplaying contradictory information. These cognitive biases don't invalidate the study of ancient mysteries, but they do suggest that we should be particularly careful about claims that seem to confirm dramatic or exciting possibilities. The most mundane explanation isn't always correct, but it's usually worth considering seriously before accepting more extraordinary alternatives. Mainstream science's approach to these questions isn't closed-minded skepticism, but rather a methodical attempt to understand the past using the best available evidence and the most reliable analytical techniques. This approach has gradually revealed a picture of ancient human capabilities that is often more sophisticated and impressive than earlier generations assumed, but it doesn't support the existence of impossible technologies or lost super civilizations. The picture that emerges from careful scientific study is of ancient peoples who were often remarkably ingenious, observant, and capable, working within the natural constraints of their time and resources to achieve impressive results. Their achievements are made more remarkable, not less, by understanding how they accomplished them using the materials and knowledge available to them. This doesn't close the door entirely on the possibility of prehistoric civilizations, but it does suggest that any such civilizations would need to fit within the constraints of what we understand about natural processes, human capabilities, and the preservation of evidence over geological time. The most interesting questions might not be about impossible ancient technologies, but about the full range of what's possible using natural materials and human ingenuity. As we reach the end of our exploration tonight, I find myself thinking not so much about whether we've answered the question of prehistoric civilizations, but about what the question itself reveals about how we understand our place in the vast story of life on Earth. Throughout this journey, we've examined evidence that spans billions of years, considered theories that stretch our imagination, and wrestled with the fundamental challenge of interpreting incomplete information about an almost incomprehensibly long past. What emerges isn't a clear answer about whether we're truly the first civilization on Earth, but something perhaps more valuable, a deeper appreciation for the complexity and mystery that surrounds us. The question of prehistoric civilizations forces us to confront the humbling reality of deep time. When we really absorb the fact that complex life has existed for hundreds of millions of years, that Earth itself has been a dynamic, changing planet for over 4 billion years, our entire perspective on human achievement shifts. We become not the inevitable culmination of planetary evolution, but rather one recent experiment in how intelligence and consciousness can emerge from the dance of matter and energy. This temporal perspective is more than just an intellectual exercise. It changes how we think about our own civilization and its place in the larger story. If we truly are the first technological civilization to emerge on Earth, that makes us extraordinarily special, but also extraordinarily isolated. We're alone not just in space, but in time, the first of our kind to ever gaze at the stars and wonder about our place in the cosmos. But if we're not the first, if intelligence and sophisticated organization have emerged before in Earth's long history, then we're part of a much deeper narrative. We become the latest chapter in a story that stretches back through geological ages, connected to other experiments in consciousness and complexity that we can barely imagine. Both possibilities are profound in their own ways. The first makes us precious beyond measure, the unique flowering of 4 billion years of evolution. The second makes us part of something larger, participants in a pattern of emergence and development that might be a fundamental characteristic of how complex systems organize themselves over time. What's particularly striking about this question is how it reveals the limitations of our knowledge about our own planet. Despite centuries of scientific investigation, despite sophisticated technologies for probing the Earth's history, we still know remarkably little about the deep past. The fossil record preserves only a tiny fraction of the life that has existed. The geological record provides glimpses of ancient conditions, but can't tell us everything we'd like to know about what happened in those vast intervals between the snapshots we can access. This ignorance isn't a failure of science. It's a reflection of the genuine difficulty of reconstructing the past from limited evidence. The processes that preserve fossils, artifacts, and geological formations are highly selective. Most of what happens on Earth's surface leaves no permanent trace. Even dramatic events can become invisible over sufficient time, erased by the constant recycling of rock, soil, and sediment that characterizes our dynamic planet. When we apply this understanding to the question of prehistoric civilizations, it suggests that the absence of obvious evidence isn't necessarily conclusive. If earlier intelligent species had followed different technological pathways than our own, if they had worked with biological systems rather than minerals and metals, if they had achieved sophistication through methods we haven't thought to look for, their legacy might be completely invisible to our current archaeological and geological techniques. This doesn't mean we should accept the existence of prehistoric civilizations without evidence, but it does suggest that we should remain open to possibilities that our current methods and assumptions might not readily reveal. The universe is under no obligation to make itself easily comprehensible to us, and the history of science is full of discoveries that challenge fundamental assumptions about what was possible or likely. The anomalies and mysteries we've explored throughout our discussion illustrate this tension between what we know and what we don't know. The Antikythera mechanism, the precision of ancient construction, the sophisticated knowledge preserved in traditional cultures, the underwater structures that might or might not be artificial, each of these represents a small crack in our understanding, a place where the evidence doesn't quite fit our expectations. Mainstream science has provided reasonable explanations for most of these anomalies, explanations that fit within our current understanding of natural processes and human capabilities. But some puzzles remain, and new ones continue to emerge as we explore more of Earth's surface and develop better techniques for studying the past. What's most valuable about these mysteries isn't necessarily solving them, but sitting with the questions they raise. They remind us that our understanding of the past is provisional and incomplete. They encourage humility about what we think we know and curiosity about what we might still discover. This perspective becomes particularly important when we consider how our assumptions about the past influence our understanding of the present and future. If we assume that technological development always follows the same pathways, that intelligence always expresses itself in familiar forms, that civilization always leaves the same kinds of traces, we might miss important possibilities about where our own development might lead. The speculative theories we explored about collective intelligence, biotechnology, and alternative technological pathways aren't just interesting thought experiments about the past, they're also ways of thinking about potential futures. If intelligence can emerge in forms we haven't recognized, if technology can develop along biological rather than mechanical lines, if civilization can organize itself in ways we haven't imagined, then our own future might hold possibilities we haven't yet considered. The cyclical theories of civilization development also offer sobering reflections on our current situation. Whether or not previous civilizations have risen and fallen on Earth, the historical record clearly shows that complex societies are vulnerable to disruption. Climate change, resource depletion, social conflict, and natural disasters have repeatedly caused the collapse of sophisticated civilizations within recorded history. Understanding these patterns doesn't provide simple answers about how to avoid similar fates, but it does suggest that maintaining civilization over long timescales requires constant attention to the conditions that support complex organization. It's not enough to develop sophisticated technologies and knowledge. Societies must also develop the resilience and adaptability necessary to survive inevitable challenges and changes. This long-term perspective also raises questions about what kind of legacy our own civilization might leave. We like to think that our achievements will be permanent, that our cities, our technologies, our accumulated knowledge will persist for future generations to discover and admire. But when you consider the kinds of timescales we've been discussing, most of what we've built will eventually disappear. The skyscrapers that seem so permanent will corrode and collapse. The roads and bridges that connect our communities will be overgrown and forgotten. Even our books and digital records will decay or become unreadable as the technologies needed to access them are lost or superseded. What might survive? Perhaps some of our more durable constructions, the concrete foundations of our largest buildings, the materials we've buried in landfills, the isotopic signatures of our nuclear activities. Future archaeologists, if they exist, might find these traces and wonder about the civilization that created them, just as we wonder about the traces left by previous societies. But they might miss the most important aspects of what we've achieved. Our art, our literature, our philosophical insights, our scientific understanding. These might survive only as faint echoes, if at all. Future investigators might underestimate our capabilities just as we might underestimate the capabilities of ancient peoples. This prospect isn't depressing so much as it is humbling. It reminds us that what matters most about civilization isn't necessarily what survives in the material record, but what it achieves while it exists. The beauty we create, the understanding we develop, the suffering we alleviate, the wonder we experience, these have value regardless of whether they leave permanent traces. The question of prehistoric civilizations ultimately leads us back to questions about consciousness, intelligence, and the meaning of existence itself. If other forms of intelligence have emerged and flourished on Earth before us, what does that tell us about the nature of consciousness? Is awareness a rare accident or a more fundamental property of complex systems? Are we unique in our ability to contemplate our own existence, or are we part of a broader phenomenon of self-aware matter? These questions don't have definitive answers, but they're worth pondering because they expand our sense of what's possible. They remind us that the universe is stranger and more complex than our everyday experience suggests, full of possibilities that we're only beginning to explore. When we look at the night sky and wonder about life on other worlds, we're asking fundamentally the same question we've been exploring tonight. Are we alone? The search for extraterrestrial intelligence assumes that consciousness and technology might emerge independently in different parts of the universe. The question of prehistoric civilizations asks whether they might have emerged independently at different times on our own world. Both questions reflect a deeper curiosity about whether intelligence and awareness are rare flukes or more common phenomena. They're both expressions of our desire to understand our place in the larger story of existence, to know whether consciousness like ours has emerged before and whether it might emerge again. Perhaps the most important insight from our exploration tonight is that this wondering itself is valuable, regardless of what answers we eventually find. The capacity to ask these questions, to imagine possibilities beyond our immediate experience, to feel wonder about mysteries we may never solve. This might be among the most remarkable achievements of consciousness. Whether we're the first civilization on Earth or the latest in a long series, we are certainly the first to ask this question in quite this way. We're the first to have developed the scientific tools and conceptual frameworks that allow us to seriously investigate deep time and contemplate our place within it. We're the first to have accumulated enough knowledge about Earth's history to recognize how little we actually know. This perspective, simultaneously humbling and exhilarating, might be our most distinctive achievement. We've learned enough to appreciate the vastness of what we don't know. We've developed the intellectual tools to ask questions that stretch across billions of years. We've gained enough understanding of natural processes to recognize how extraordinary the emergence of consciousness actually is. As we continue to explore our planet's history, as we develop new techniques for studying the past, as we search for signs of life beyond Earth, we'll undoubtedly discover new mysteries and perhaps resolve some old ones. But the fundamental questions about consciousness, about our place in time, about the meaning of existence, will likely remain open, inviting each generation to wonder and explore. That ongoing invitation to wonder might be the most valuable thing we can pass on to whatever comes after us. Whether future intelligence emerges from our own descendants, from other species on Earth, or from entirely different evolutionary pathways, the questions we've been exploring tonight will likely remain relevant. The mystery of consciousness, the puzzle of our place in deep time, the wonder at existence itself, these seem to be enduring themes that transcend any particular form that intelligence might take. So perhaps the question of whether we're the first civilization on Earth is less important than what asking the question reveals about who we are and what we're capable of becoming. In our willingness to consider these vast possibilities, to sit with uncertainty, to remain curious about mysteries we may never solve, we demonstrate something remarkable about consciousness itself, its drive to understand, to wonder, and to reach beyond the boundaries of immediate experience. In the end, whether we're alone in time or part of a larger story, we are here now, aware and questioning, capable of contemplating billions of years of history and imagining futures we'll never see. That capacity for wonder, that ability to ask questions that stretch beyond our own existence, perhaps that's what makes any civilization, whenever and however it emerges, truly extraordinary.